Okay, so we're going to go through some of the examples from the level 4 uncertainties problems that you were set. These were looking at specifically combining uncertainties, but combining them, calculating quantities that often involved either a squared or a cubed value. Okay, so all of these needed you to start off by finding the formula that you required for that particular quantity. All right, so in this first example, it was pressure that we were after. So you needed to recall that pressure was force divided by area. All right, now we've got our force because that is in fact our weight that we've got here, but we haven't got our area because we have been given a length. So our area is our length multiplied by our length, or our length squared. So the first thing to do is actually calculate the value for pressure. Now we know what it is, okay, because you can see from our options that it's 5.6, but nonetheless we need to work it out properly so that we can do the rest of the problem. So let's start by working out the actual area that we're looking at, okay? So we know that area is L squared, as we've said, and it's 5 centimetres, so that's 5 times 10 to the minus 2 squared, giving us an area of 2.5 times 10 to the minus 3 meters squared. All right. Then we can now feed that into our formula for pressure. So we've got 14 newtons divided by 2.5 times 10 to the minus 3, giving us a pressure of 5,600 pascals, which is equal to 5.6 kilopascals. No surprise there. We can see that's our option, so that is fine. What we now have to do is, in order to work out the absolute uncertainty in the pressure, we have to first work out the total percentage uncertainty in the pressure. To do that, what we have to do is work out the percentage uncertainty in each of the quantities that go into calculating pressure. So we need to work out the percentage uncertainty in force and the percentage uncertainty in area. So if we do the percentage uncertainty in F, first of all, we take our absolute, which is 0.5 newtons, we divide it by our actual value of 14, we multiply that by 100, and that gives us a percentage uncertainty in the weight, or in this case our force of 3.57%. Now we have to work out the percentage uncertainty in our area. Okay. Now the problem that we've got is our area is made up of our percentage uncertainties in our lengths. Okay. So to work out the percentage uncertainty in area, we have to first work out the percentage uncertainty in our lengths. All right, so rather than being able to do percentage uncertainty in area, we work out the percentage uncertainty in our length. And again, we do that the same way. So we take our absolute, we divide it by our value, and we multiply it by 100, which gives us a value of 2%. Now, that's the percentage uncertainty in one value of L. As we've already said, the area is calculated by L squared. Because that is L times L, then what we have is we have to sum the individual uncertainties associated with L. So that means that the percentage uncertainty in A is simply equal to 2%, which was our percentage uncertainty in the first value of L, plus 2%, which is the percentage uncertainty in our second value of L. You don't multiply uncertainties, okay? To work out area, we have two quantities, and therefore the total uncertainty is the sum of those two. So we now know that we've got 3.57% uncertainty in weight and a total of 4% uncertainty in our area. So the total percentage uncertainty in our pressure is going to be 7.57%. Our final step now, to allow us to work out the absolute uncertainty in our pressure, is to work out 7.5% of that value that we worked out. Okay, so working out 7.57% of 5,600. So if we do that and we say, well, okay, 5,600 multiplied by 0.0757, then what we end up with there is we end up with 423.9 pascals, which is equal to 0.424 kilopascals. So what that means is that our pressure is 5.6 plus or minus 0.4 kilopascals. So our answer must be D. When it comes to working out the value for the volume of the cylinder, we approach this in exactly the same way as we did with pressure. This time, however, the formula that we're looking for is pi r squared h. Okay? Now the difference here is that we have been given a value for D, not a value for R. Remember, D would be 2 lots of R. Okay? But the thing to remember is that when you are given D's or R's, whatever the uncertainty and therefore whatever the percentage uncertainty in D is, it is the same as the percentage uncertainty in a value for R. Okay? So we still approach this in the same way. We start by actually working out the volume of our cylinder. Okay? So in order to do that, we need to take the pi, as we've said, the radius, so that is our 35.1 times 10 to the minus 3. Okay, we divide that by 2 because 35.1 is our diameter, squared, multiplied by our height, which is 35.1. No, it isn't. Change that away. It is 11.8 centimetres, so 0.118 metres. That gives us a value for volume of 1.14 times 10 to the minus 4 metres cubed. And again, we can see that we know that's the right answer because that features in our options below. Now we work out the percentage uncertainty in our height. Okay, so again, 0.1 divided by 11.8 multiplied by 100 gives us an uncertainty of 0.847% in H. Notice I haven't had to convert into meters for these because it's a ratio. Because both of them are measured in centimeters, it's perfectly okay to work out the percentage uncertainty, leaving them both in centimeters. If we then repeat that process, but this time we do this for R, okay, and as I say, it's the same as the percentage uncertainty would be for D, which means that we take 0.1 divided by 35.1 times by 100, and that gives us a value for that of 0.28%. Therefore, our total percentage uncertainty is the 0.847 plus 0.28% for the first R, but an additional 0.28% for the second R, okay? Because remember, as I've said previously, in working out volume, it's pi multiplied by R, multiplied by R, multiplied by H. So we add together the 3 uncertainties from the 3 values that we use. So that gives us a total percentage uncertainty of 1.417%. So then our last step is to say, well, okay, then we take our value for volume of 1.14 times 10 to the minus 4. We multiply that by 0.01417, and that gives us an absolute of 1.62 times 10 to the minus 6, which is very roughly 2 times 10 to the minus 6. When we then look at our options, what we can see therefore is that our value for volume becomes 1.14 plus or minus 0.02 times 10 to the minus 4 meters cubed. So our answer in this case is A. When we come to question 3, I'm not going to go through the whole of this one. I am simply going to insert the worked answers, but just to reassure you, it's exactly the same process, but this time we've got half mv squared. Okay, so you have to work out the percentage uncertainty in m, you have to work out the percentage uncertainty in v, and then when you come to work out the total percentage uncertainty, it will be equal to the percentage uncertainty in m plus 2 lots, once again, because we've got V squared. So percentage uncertainty in V plus percentage uncertainty in V. Okay, so you will find in a moment that I will insert the actual worked answers for you to have a look at, so you can pause the video if you feel absolutely necessary. Okay, so that you can work it through, but this process is exactly the same as the first two, which is why I'm not going to show you the whole thing again. But the answer that we should come up with is 0.13 plus or minus 0.01 joules. When we came to question 4, we were now raising things to the power of 3. So we're looking for the volume of a marble and therefore the volume of a sphere, which is 4/3 pi r cubed. Okay, so once again we are given a diameter, not a radius, but remembering that the percentage uncertainty in a diameter will be the same as the percentage uncertainty in a radius. Okay, so first things first, actually calculate the volume. So to do that, we have 4/3 pi, and then our radius, so 1.33 times 10 to the minus 2 divided by 2 cubed. All right, that gives us a value for volume of 1.23 times 10 to the minus 6 meters cubed. Although if you actually look at the options for the question, I've defaulted to converting into meters, which is what we should do, but actually the question asks for it in centimeters cubed. So 1.23 times 10 to the minus 6 meters cubed is equal to 1.23 centimeters cubed. If we then work out the percentage uncertainty in R, we take that to be exactly as it was for D, so 0.01 divided by 1.33 times by 100, which gives us a value of 0.752%. Okay, in this case, because our volume is 4/3, which has got no error associated with it, pi, which has got no error associated with it, but then we've got 1, 2, 3 lots of R, then our total percentage uncertainty is 0.752 plus 0.752 plus 0.752. I know I could write multiplied by 3, but I don't want you to get confused by multiplying uncertainties, because you shouldn't. You should always add them, which is why I'm writing it out this long-winded way rather than simply saying 3 lots of 0.752. So that then gives us a total percentage uncertainty of 2.256%. And then if we take that value of 1.23 and we multiply it by 0.02256, that gives us an absolute of 0.02779 centimeters cubed. And if we look at our options, that means that the volume of our marble is 1.23 plus or minus 0.03 centimeters cubed. Okay, so it is in fact option D. And question 5 was bringing in a few more. This was not only combining a raised power, but we also had multiple quantities besides the 2 that we've been using so far in the previous examples. Okay, so this equation was requiring you to remember the link between resistance and resistivity, and if we rearrange that, resistivity is resistance multiplied by area divided by length. So that is what we were looking for. Now, before we could go any further, we needed to work out the area, okay, and we do that using pi r squared as always. So there we have our 0.15 times 10 to the minus 3 divided by 2 all squared, which gave us an area of 1.767 times 10 to the minus 8 meters squared. From that, we can work out our value for resistivity. So we had 69 as our resistance, multiplied by our area, which we've just worked out, and divide that by our length, which was 85 centimetres, giving us a value for rho of 1.43 times 10 to to the minus 6 ohm meters. And again, we can see that that's right from the options we've got below. So now, individual percentage uncertainties for each of those three quantities. So let's start with R, because that's nice and straightforward. 1 over 69 times by 100 gives us 1.45%. L, which comes out as 0.235%. And then lastly, we have to look at our percentage uncertainty in area. And remember, as we've set up at the top, area is pi multiplied by r multiplied by r. So our percentage uncertainty for area is equal to the percentage uncertainty for r, that should be little r, sorry, plus the percentage uncertainty for little r. All right, so what that is that's the same as our diameter, and therefore that is 0.01 divided by 0.15 times by 100, which is equal to 6.67%, but that's the percentage uncertainty in R, and therefore the percentage uncertainty in A is 6.67 plus 6.67, which comes out at 13.3%. So our total percentage uncertainty is the sum of the resistance, the length, and the area, which gives us a total percentage uncertainty of 15.02%. And when we then take our value of 1.43 times 10 to the minus 6 and we multiply that by our value for percentage, we end up with an absolute uncertainty of 2.15 times 10 to the minus 7. So when we look at our options down here, what we have is we have a value of 1.4 plus or minus 0.2 times 10 to the minus 6 ohm meters. Okay, so if you need to go through this, then run through any of the video again, pausing it and stopping it as you may need to. Okay, remember you've also got the worked answers that I've written for you, so it's really important that you make sure you are confident in tackling these.